US Physics Olympiad year 2021 USAPHO final round. This year all competition was held in one day. There were given 3 big problems with many questions, so it was given 5 hours for all day. If you need more interesting problems, just subscribe for this channel. Problem 1. The jet stream. The jet stream is an eastward with a current that moves over the continental United States at an altitude of 23 to 35,000 feet. The range of typical cruising altitudes of commercial airlines. This strong current affects the flight times significantly. Flights traveling eastward fly significantly faster than flights traveling westward. This problem consists of 2 independent parts. In the first part, you will consider a simple model for airplane flight. In the second part, you will determine the jet stream speed on a fictitious planet called Orb. Part 1. The power that a plane expends is used both to combat drag and to generate lift. Throughout this part of the problem, you may assume that the plane travels without horizontal velocity v-rel relative to the air. The density of air is rho air. The mass of the plane is m, and the cross-sectional area of the plane is ACS. Question A. The drag force on an airplane is given by F drag equal -1/2 CD rho air ACS multiplied by absolute value for v-rel and multiplied by vector v-rel, where CD is the drag coefficient, which depends on the shape of the plane. Write an expression for the power expended by the airplane to combat the drag force from the air. Question B. Airplanes generate lift by deflecting air downward. 1. Estimate the air mass per unit time which is deflected by the wings of the plane. 2. Estimate the power expended by the plane for lift. Question C. Estimate the speed at which an airplane flies relative to the air by minimizing the power expended by the plane. To get a numeric answer, you may use the following parameters. Mass of plane approximately 8 by 10 power 4 kilograms. Raw air is about 1 kilogram per cubic meter. CD about 10 power -2. ACS is about 100 square meters. Next, we estimate the jet stream speed using flight times. Because the jet stream speed on Earth varies greatly with the location, time of year, and climate effects such as El Niño and La Niña, you will instead consider the fictitious planet Orb, where the jet stream is eastward and uniform in the region of interest. At the end of the problem is a map of the region, whose area is much smaller than the surface area of Orb. It means you can neglect the curvature of Orb. Part 2. At cruising altitude, we assume all airplanes travel at a fixed speed v-rel relative to the air. This is not necessarily the same as your answer to Part 1 Question C, which was just a rough estimate. Additionally, we assume that flights occur in 3 stages. First, taxi and takeoff. Second, flight at cruising altitude. Third, landing and taxi, and that Stage 1 and 3 take a fixed total time t0 for every flight. Question A. Suppose a plane at a cruising altitude is traveling at an angle theta away from due east relative to the ground. What is the speed of the plane relative to the ground? Give your answer in terms of v real, theta, and vw, the speed of the jet stream relative to the Earth's surface. Question B. If the plane travels a distance d, what is the total travel time t, including taxi, takeoff, and landing? Question C. Below we present some data on airplane flights on planet Earth. Each of the flight times shown below has an independent uncertainty of delta t equal 5 minutes. From the data and the map, determine VW and VREL, giving your answer in kilometers per hour with the uncertainties. Indicate clearly what two quantities you are plotting against each other on each graph that you plot. These are data and a sheet to work with this problem. US Physics Olympiad, year 2021, USAPHO, final round. Problem 2. The dark forest. Dark matter could be made of hypothetical extremely light particles called axions. Because individual axions are so light, experiments do not search for individual axions, but rather for the classical axion field formed by a large collection of axions, which oscillates as a function of t equal a0 sine omega t. This is analogous to how a large collection of photons can form a classical electromagnetic field. In the presence of a magnetic field B and an axion field A, the axion field produces an effective current J equal G A dot B, where we define A dot as first derivative from A by time d. The effective current produces electromagnetic fields in exactly the same way as ordinary current, though it does not come from the motion of actual charges. Experiments can search for axion dark matter using systems which are resonantly driven by this current. You may use fundamental constants in your answers such as speed of light, c, h, that's a Planck constant, E, that's a charge of electron, G, that's a gravitational constant, μ0, that's magnetic permeability for vacuum, Kb, that's Boltzmann constant. You do not have to provide numeric answers unless asked. When asked to estimate, you may drop constants of order 1. The numeric values provided below are from standard references where h, c, μ0 and epsilon 0 are set to 1. To get correct numeric results, you must restore these factors yourself. Part 1. First, we will describe some physical properties of the axion field. A. Consider a single axion at rest with mass m. Find its associated angular frequency omega. This will be the angular frequency of the corresponding classical field when there are many axions. B. Suppose dark matter is distributed spherically symmetrically in the galaxy with a uniform density ρ. The solar system is a distance r from the center of the galaxy and orbits around it with a period t. Neglecting everything besides dark matter, find the dark matter density ρ. C. The energy density of the axion field is m square a0 square over 2h power 3 c. Find the axion field amplitude a0. D. The radius and the period of the Sun's orbit, as well as the typical axion mass are r equal 2.5 by 10 power 20 meters, t equal 7.1 by 10 power 15 seconds, m equal 1.0 10 power negative 9 electron volt. Numerically compute the axion field amplitude a0. E. In this problem, we treat the axion field as spatially uniform within a terrestrial laboratory. To verify that this assumption is reasonable, numerically estimate the axion field's wavelength, lambda, assuming the axions have the same galaxy speed as the Sun. F. In part A, you found omega by neglecting the axion's speed. In reality, the axion's finite speed changes the frequency to omega plus delta omega in the frame at rest with respect to the galactic center. Numerically estimate delta omega over omega to show that it is reasonable to neglect this effect. Next, the abracadabra experiment, where abracadabra is abbreviation for this one. Currently taking data at MIT is a toroidal solenoid with the inner and outer radius r in and r out and the height h. You may assume that h much greater than r out for simplicity. A superconducting wire carrying current I wraps n times around the toroid, where n is high enough to neglect the discreteness of the wires. A circular pickup loop with a radius slightly less than r in is placed at the center of the toroid. Part 2. Now we will find the axion signal generated in the abracadabra apparatus. A. Find the magnetic field B as a function of r inside the toroid due to the superconducting current. B. The superconducting wires lose their superconductivity when exposed to a magnetic field greater than B max. Find the maximum possible current I max that can be used and assume this current is used in later parts. C. Assuming that omega is small, find the magnetic flux Fb as a function of t through the pickup loop due to the axion field in terms of A0, G, omega, B max, and the dimensions of the apparatus. You may ignore any currents induced on the surfaces of the superconducting wires. According for them makes the problem much harder, but does not substantially affect the final result. D. If omega is too large, the result above breaks down due to radiation effects. Estimate the frequency omega c where this happens. E. Using the design values r in equal 0.5 meters, r out equal 1 meter, and h equal 2 meters, estimate the numerical value of omega over omega c. F. Let F0 be the amplitude of the time-varying axion flux. Using the typical values B max equal 5.0 Tesla, G equal 1.0 by 10 power negative 16 giga-electrovolts in power negative 1, and your previous results, compute the numerical value of F0. Next, the pickup loop has inductance L and is attached to a capacitor forming a circuit with a resonant frequency equal to the axion frequency omega. The circuit also has a small internal resistance R in series and is at temperature T. The axion signal can be detected by monitoring the current in the circuit. The main source of noise is thermal noise, which causes fluctuations in the current. Part 3. We will now estimate the sensitivity of abracadabra to axions. A. The axion produces a current which oscillates sinusoidally. Find the signal current amplitude Is in terms of omega f0 and the circuit parameters. B. Find the average value of the current squared, I square, in the circuit due to thermal noise. C. At any moment in time, the noise current is oscillating sinusoidally with a typical amplitude In equals square root from min I square, which is much larger than Is. However, the phase of the noise current also fluctuates randomly, so that after a typical time Tc, its phase will be roughly independent of the phase it had before. Find an estimate for Tc in terms of omega and the circuit parameters. Hint: at any given moment, the thermal noise current is simultaneously being produced by the random motion of electrons in the circuit and damped by the resistor. D. Suppose the experiment runs for a total time Te much greater than Tc. Roughly estimate the average amplitude of the noise current over this period of time. E. The axion is detectable if the signal current amplitude is larger than the average noise current amplitude, and the circuit parameters are L equal 1 millihenry, R equal 10 milliohm, and T equal 0.1 Kelvin. Roughly numerically estimate the time needed to potentially detect the axion. Hint: if your answer seems strange, note that in reality the axion's phase also fluctuates over time because of the effect of part 1f. In addition, we don't know omega ahead of time, so the experiment needs to be run many times. We ignored these effects here to keep things simple. US Physics Olympiad, year 2021, USAPHO, final round. Problem number 3. Great Hall. The classical Hall effect was first measured by Edwin Hall in 1879, shortly after the publication of Maxwell's equations. In all parts of this problem, materials contains NV electrons per unit volume, and each electron has charge QE less than 0 and mass ME. You may use these quantities in all of your answers. We will begin by investigating the implications of the classical Hall effect. Part 1. An infinite plate in the xy plane with a thickness d in the z direction is placed in a uniform magnetic field B equal B multiplied by unit vector z as shown. An electric field E equal E multiplied by unit vector x is applied in the plane of the plate and the system is allowed to reach a steady state. Question A. If the electrons have velocity v at steady state, what is the current density J Recall that J is defined as the total flow of a charge through a unit cross-section area per unit time. Question B. In the Drude model, electrons are subject to both the Lorentz force and damping force negative gamma V, where gamma is a constant that depends on the material. In the above system, what is the current density in the steady state? Give both the magnitude and the direction of J in polar coordinates. Question C. Compute the electrical resistivity ρ0 equal limit for B going to 0 for relation E over absolute value Jx, and the transverse Hall resistivity ρh equal limit for gamma going to 0 for relation E over absolute value Jy. Question D. A Hall effect sensor detects the strength of magnetic fields. Consider the following circuit consisting of a square plate of side length L and thickness D in a perpendicular uniform magnetic field B. A longitudinal EMF E is applied to the plate. At steady state, a Hall voltage VH is measured across the plate due to the buildup of a charge in either side of the plate. If the electrical resistivity of the plate at zero magnetic field is ρ0, what is the Hall voltage VH and the current I through the plate? Express your answer in terms of ρ0, E, B and the dimensions of the plate. Experiments in the 20th century revealed that in many materials the Hall resistivity could only take certain discrete values. We will now show how this follows from Bohr quantization. These next parts are independent of the first part of the problem. Part 2. A zero resistance loop of a wire of radius r and the cross-sectional area AW carries counterclockwise current I. Solenoid through the middle of the loops carries magnetic flux F out of the page, which we define to be the positive Z direction. Question A. If the electrons all have the same speed, what is the angular momentum of each electron? Question B. If we allow the flux in the solenoid to change, the usual mechanical angular momentum L of each electron is not conserved. Instead, quantity called the canonical angular momentum L can equal L plus C QEF for some constant C is conserved. Find C. Question C. The Bohr quantization condition says that for a closed circular orbit an integer number of the de Broglie wavelengths must fit in the circumference. The de Broglie wavelength is lambda equal h over p can, where h is Planck's constant and the p can equal L can over r is the canonical momentum. For a given solenoid flux F, what is the set of allowed mechanical angular momenta L? Question D. What is the momentum possible change in the magnetic flux for which the same set of mechanical angular momenta is allowed? This is known as a flux quantum. Part 3. Now consider an annulus held perpendicular to a fixed uniform external magnetic field B, and suppose an additional tunable magnetic flux F threads the center of the annulus, with the both pointing out of the page. The annulus has a transverse Hall resistance RH and EMF of E around the annulus generates a perpendicular current E over RH via Hall effect, and you may neglect its self-inductance. Question A. Suppose F begins to increase slowly and steadily in time. After a short time, the electrons will begin flowing steadily from one side of the annulus to the other. Do the electrons move inward or outward? Justify your answer. Question B. If the threaded flux increases by delta F, how many electrons pass from one end of the annulus to the other? You may use RH among other variables in your answer. Question C. As we show it in 2D, if the magnetic flux changes by the flux quantum FQ, the allowed orbits from Bohr quantization are unchanged. Quantum mechanics thus tell us that in conventional materials, if the magnetic flux changes by FQ, an integer number k of the electrons must pass from one edge to another. What constraint does this place of the Hall resistance?